Think about the last time you took some medication. Maybe it was an ibuprofen at breakfast this morning, or for a headache, or maybe some prescription drugs that you take regularly. Have you ever thought about the testing process that medication went through before clinical use? Drugs are first tested on cells in a petri dish, as you can see in the top left, followed by trials on animal models and then human clinical trials. Animal models are needed because cells behave differently on two-dimensional environments compared to three-dimensional environments. But animals are different than humans. What if we had human model tissues or imitation tissues that we could test drugs on? Let's say a piece of lung tissue or liver tissue. Wouldn't that be useful? This is where tissue engineering comes in. In tissue engineering, scaffolds are used to temporarily support cells, just as how it's in construction, scaffolds temporarily support buildings. The scaffolds support the cells, provide a three-dimensional environment, and provide biomechanical and biochemical cues to allow the cells to make their own native supporting structures, also called the extracellular matrix. At this point, the scaffolds can then degrade, leaving behind a new piece of tissue. One of the ways to do this is by forming nanofibers, which you can see in the top right. And these nanofibers are beneficial because they do a good job at mimicking the native extracellular matrix. However, they also form very dense meshes, so the cells cannot properly infiltrate the scaffold and just sit on top, as you can see in the bottom left, which defeats the whole purpose of having a three-dimensional scaffold. So my research looks at increasing the porosity of these scaffolds so the cells can properly infiltrate, and this assists in the formation of a 3D piece of tissue. One of the ways in which I do this is I make the scaffold out of two materials. One of these materials is water soluble. So when the scaffold gets left in some water and exposed to ultrasound waves, the water soluble material dissolves, ideally leaving behind a looser, more porous scaffold. And then in this porous scaffold, the cells can properly grow and recreate their own matrix in the forming of these new tissues. So technologies like these provide more tools in the drug testing process. So we have another step and we can catch bad drugs earlier on before they reach the clinical testing phases. This has the potential to reduce costs and make the drug testing process more cost-effective, which then maybe even has the potential of making drugs more affordable to the end user. And that's something that affects us all. Thank you.